think we're about time. Get started. So, our first speaker in the afternoon session is Clayton Ramsey, and he is a second-year PhD in Professor Lydia Kavraki at Rice University. So Clayton's research are mostly focusing on reactive planning and with applications in robotic manipulations. And today's talk, he's gonna show us his recent progress on using Rust programs, using Rust in programming planning algorithms in manipulations. So the floor is yours.
Thank you. Thank you. So as you said, today we'll be talking a little bit about my work on trying to make robot planning more flexible and more performant, especially in Rust. And we'll cut straight to the good part. Our work is really helping robots to plan in a dynamic and unmodeled environment where they have no real knowledge of what the scene is like beforehand, and where there's very, very tight bounds on how much time they can spend planning before they have to act. In the demo that you just saw, the robots were doing motion planning from scratch at 60 Hertz. So from our point cloud camera, which is on the ceiling, we get a new point cloud every 16 milliseconds, once every 16 milliseconds or 60 times per second. And then in that 16 millisecond window, we're able to construct a new motion plan from scratch and then begin executing that motion plan before that window is ended. And this is actually a very, very tight window if you're familiar with the kinds of time requirements for motion planning. It's surprisingly common to have motion planning algorithms that take on the order of fractions of a second or multiple seconds to execute. So fitting in this really tight time budget is extremely difficult, and I'll explain a little bit how we made this happen for the rest of this talk. But at the heart of this is really trying to make sure that we can do motion planning fast and efficiently. And so we'll explain a lot in detail. In this talk, we're going to be covering two different topics. One is sort of the original data structures work that went into that demo, talking about how we can model our world using sensor data in a way that is very performant and very efficient, with very strong guarantees about correctness. And the second is a more general approach, looking at how we model motion planning in general without losing any performance guarantees. So we're able to be general across many robots and environments, but we still can achieve really high performance. And let's start off with this data structures work. First, let's review a little bit and talk about motion planning. In short, motion planning is a broad collection of algorithms and problems, but they all kind of look the same. We're usually given a start state, which is QS, and an end state, which is QG, and we're asked to find a collision-free path between these two states. And there are lots and lots of algorithms, but the ones that I'm thinking about today are called sampling-based planners. And once again, sampling-based planners are astonishingly diverse, but if you squint really hard, they all kind of look the same. If you look at your configuration space and you zoom in on what each planner is doing, they're really just sampling points in the configuration space, connecting them with small direct motions, and then creating this graph out of these connected motions. So if we want to be able to do planning, we have to be able to do these very primitive operations, sampling random configurations, testing if they're valid, and then checking if the motions between these configurations are valid really, really fast. And in practice, that means we're working with collision checking. So we need to be able to do collision checking to test if these configurations are valid very, very quickly. And if you want to do fast collision checking, there are lots of options, but one of the things that's particularly interesting recently is single instruction, multiple data parallelism. A SIMD, single instruction, multiple data instruction, is a special kind of instruction that's found on nearly every computer in the world. They are unlike your ordinary scalar add instructions. So for instance, if you were trying to add two numbers, you could take two numbers, x1 and y1, and add them together and get one result, z1, in a single instruction cycle on your CPU. But using a SIMD instruction, you could take two lists of four numbers, x1 through 4, y1 through 4, and then add them together pairwise and get four results, z1 through 4, all on the same instruction cycle. So this is very promising. We get basically free speedups in all of our code. But the thing that makes this really hard to work with in practice is that SIMD instruction parallelism is much more restrictive than, say, a threaded parallelism model, or even the SIMT, single instruction multiple thread model, that you see on GPUs. So we have to design our algorithms with this kind of parallelism in mind. And there is some existing work in this area. Some of my collaborators at the Kawaki Lab published some really excellent work on accelerating motion planning in well-perceived environments in parallel using SIMD. But the problem with that work was that it could only ever interact with a world that was explicitly modeled, like, say, those brightly colored objects that you see in the demo. The problem is you usually don't get an explicit model of your world. You simply get whatever comes out of your sensors. So for this talk, we'll be focusing on one kind of perceived world model, which is just a point cloud. So that can come out of your depth camera, it can come out of your LiDAR, we don't care where. But as long as we get points in the 3D space, we would like to be able to plan against those points in 3D space without having to go through the step of modeling them as collision geometry directly. To start off, we can make a simplifying assumption to make this problem of collision checking between our robot and our world model a little bit more efficient. So let's take our robot and we'll model it as some set of spheres. And we can do this at compiled times. This is pretty easy to do. And once we have this set of spheres in our robot, we can reduce our point cloud collision checking model from a brute force search where I have to check my robot against every single point in the cloud to a nearest neighbor search. To do that, we can take one sphere of our robot, find the nearest neighbor from the sphere of our robot to the point cloud, and then once I have both of those, I can simply check how far that nearest neighbor is from the center of the sphere and ask, is that further than the radius of the sphere? If it's too short, then it's in collision, and if it's too far, then none of the point clouds in collision. And we repeat that process for every sphere of the robot. And this gets you down from n squared to n log n. And if you're interested in doing nearest neighbor search, the first data structure you might reach for would be something like a KD tree, which is a space partitioning tree that chops up the entire space into little rectangular prisms called cells. Each of these cells contains one point, and then we use these separating planes between these cells as branches in a search tree. And then to find our nearest neighbor, we have to do a sort of branch and bound search across the entire tree. And this would be nice. It would be great if we could use this with our SIMD parallelism. But the big problem is this is a very branchy, very backtrack heavy approach. And it's impossible to implement a traditional KD tree with that style of parallelism we're interested in. So we need to design a KD tree which is very fast, very performant, and works with SIMD, but somehow doesn't have this branchy backtracking step, which seems impossible. And if you assume it's impossible, well, maybe we can just try cheating. So let's try doing approximate nearest neighbors. And that's promising. It makes it really, really easy to implement. So if we're doing a KD tree search, we can use a sort of vector-backed layout for efficiency. And then we can do our approximate nearest neighbor search really, really fast. We can actually fit the entire nearest neighbor search algorithm in a single slide, which is really nice. But the problem is, and even better, before I get to the problems, even better is that this search algorithm has an explicit bound on how many times we do that main while loop. So we can actually parallelize the search algorithm. So we can search through this tree in parallel across a batch of spheres of our robot, and we can get great speedups. In practice, this means that we get speedups on the order of 10x on that search algorithm. And we find that the SIMD parallelism doesn't get you huge benefits in this specific case because most of our time is spent for waiting for memory to load, but we can get better speedups later, I promise you. But the problem with that sort of naive approach of doing your approximate classification by doing a single bounded pass through the tree is that it's just crazy inaccurate. So this is one from some real data that I worked with. And what we found was that if you're doing this approximate approach, you get off by 10 centimeters or about 6 inches, 5 inches, 80% of the time, which is completely unacceptable if you want to actually do motion planning in the real world. So we have to throw all this out, maybe keep the good ideas of that really fast search algorithm, but somehow we have to find a way of making this correct, but also fast. And so our proposal is a new data structure called the collision affording point tree. And the big insight here is that we can use the existing robot's geometry and use that to inform the shape of our data structure. So we're going to start by looking at our robot again, and we're going to pick the biggest sphere on our robot. And we'll say that that robot's biggest sphere has radius Rmax. And we know what our robot looks like at compile time or configuration time. So this is completely without loss of generality. We can use this on any robot we want. And then once we have that radius Rmax, we can really be clever about how we build our KD tree. So let's look at one cell of the KD tree. That cell contains one point, but there are other points in the neighborhood surrounding that cell that could be in collision with a sphere that we classified in that cell with our very fast search algorithm. So let's, at construction time, before we even search through the tree, write down all of the points within that local neighborhood, within a radius of Rmax from that cell, and store that in a contiguous buffer that's really easy to access at high speed. And then for every single cell in this tree, we're going to repeat that process, finding all the neighbors within that radius Rmax, storing them in a contiguous buffer, and then at search time, instead of having to search through many different branches in a very unpredictable pattern, we can do a very simple linear scan through these candidates for collision. And as long as the cells are sufficiently big compared to Rmax, and so we don't include all of these points in this small neighborhood, we can guarantee that that linear scan is going to be pretty small, and so we can guarantee this is going to be pretty fast. And so we decided to implement this, and we got good performance results. And then we went to go put it on a robot, and we had to go write in C++. The main reason was the motion planning system that we were working with at the time was written in C++, and so we had to make it work. I came across a few interesting bugs in LLVM at the time. There were some cases where we just got no speed up from SIMD at all, but in practice, we actually did get some good speed ups. When we benchmarked the C++ implementation, we found some really great results. So compared to two competing methods, octamaps, which are a voxel-based method that represents the world as sort of a tree of cubes, and nanoplan, which is a traditional KD tree, we had collision checking speeds over an order of magnitude faster. So from hundreds of nanoseconds down to less than 10 nanoseconds for our SIMD parallel implementation. And that's really great. And when we put it into our robot planning systems, we found that we got incredibly good planning times, down from, say, 400 milliseconds for the fetch on octamaps, all the way to 20 milliseconds on fetch, and then under 10 milliseconds on the UR5 and Panda robots. And for the UR5 and Panda, we've highlighted that total end-to-end planning time from perception all the way to action. And we have that planning time fast enough that we can do it online with a 60 hertz camera. So that's really excellent results, and we were really happy with that. But I was not so happy with that because I did not really like doing all of my planning in C++, and I did not like writing in C++. And so the next part of this talk is going to focus on doing all of this motion planning in a sort of Rust-friendly and low overhead framework. And the reason I got into this sort of building my own framework approach is that writing in C++ kind of sucks, especially when you're talking about building very large software with lots of dependencies. I spent on the order of 2 or 3 months gluing together dependencies and fighting through CMake errors, and I decided that was not a good use of my time. And so I eventually threw everything out and rewrote it all. But if we want to rewrite everything, we want to do it right. And we want to be general across all our robots and all our environments and all our planners and so on. And I'm a perfectionist. So we had to start thinking about the kinds of robots we're working with. Every robot's a little bit special in that it has a different set of possible configurations it could be in. And not only that, the space of configurations looks entirely different for every robot. So for a simple 3-degree of freedom manipulator, like this little chain arm, you have 3 dimensions and you have a 3-dimensional configuration space. If there were 4 joints, you'd have 4 dimensions and so on and so forth. But even when your robots have the same number of dimensions, they might also have different looking configuration spaces. So my Roomba over there, sketched beautifully, as you might imagine, has the same 3-dimensional configuration space, but the ways that you can move through it are much different from my 3DOF arm, because now I can spin around as many times as I want and go in a loop. And I'm also not holonomic in the sense that if I'm not allowed to translate sideways, there are certain paths in this configuration space that I can't take. So we have to capture that in the planning framework somehow without any cost. And that's going to be really, really hard. And it gets worse. Planners are all kind of weird and special in their own ways too. So you've got your traditional rapidly exploring random trees, which require us to do nearest neighbor search in the configuration space, and from a given point in configuration space, propagate out towards a target. And then there are other planners, like PRM, which still require nearest neighbor search, but are a little stronger in their requirements. So now I have to take 2 given configurations and find a contiguous path between them. And then some planners are just weird, like KPiece, which doesn't require nearest neighbor search, but does require us to be able to project down to lower dimensional spaces and then roll out operations based on velocity inputs. And so all of these planners are different, all of these robots are different. How do we capture that, preferably inside of Rust's compilation system, so that we can force the user to write correct code, or at least mostly correct code, but still not give up on any performance? And the obvious result is, well, just use the type system, use traits. And this actually is really effective. So we might write a trait for metrics, which can tell us how far 2 configurations are from each other. Or we can write traits for interpolating between 2 configurations. Or we can write traits for strictly linear interpolation, which is a little stronger than any arbitrary interpolation. And on top of that, we can write traits that capture implementation details of our planners. So for instance, in non-Euclidean spaces, KD trees just don't work. So we have to be able to be generic over the nearest neighbor search algorithms we even use in, say, PRM and RRTs. And so once we've captured all of this information about our robots and our spaces and the things we can do to them, we can generate really, really generic functions, which still are very performant to compile time. So if I have a planning function like adaptive DDRRTC, you don't have to know what it is, but we can always capture the exact information we need to know about our configuration space and our robot and our environment to be able to tell if we can use this planner. In our case, it might include something like the ability to interpolate between 2 points in the space, maybe some kind of nearest neighbor facility, the ability to validate edges and transitions between configurations, the ability to have a metric with a known maximum or known upper bound, and all of these weird, odd little requirements on this metric as well. And finally, all of my planners in this implemented framework also take in a timeout condition. So we're also being able to be generic over all the possible ways you could use this planner and all the frameworks that could work in. And in particular, because I've made all of this so generic, it's very easy to make something that is embeddable in very low overhead runtimes as well. This planner doesn't require any access to, for instance, the standard library. So if you are familiar with Rust, you know that embedded programmers really need to work in no standard. So we can, because we're very generic, we can say that we can build this entire planner without using the standard library, without using the operating system. And so you can put it on your tiny little embedded STM32 if you really, really wanted to. I wouldn't recommend it though. And on top of that, it's much easier to produce correct results using Rust. So as I mentioned earlier, if I have a KD tree, the traditional KD tree search algorithm requires you to be able to use a direct distance metric from a little cell in your space to a point. And that distance from a cell to a point often assumes in real KD tree implementations that you can just project the interior of the cell onto the point or the point onto the cell, and that tells you your distance. But in practice, that only works in Euclidean spaces. And so we can capture that information at compile time and say, no, if your space is Euclidean, you may not use this nearest neighbor structure. You have to use something else that's more generic. And the nice thing here is that hopefully, if this gets published and sent out to the real world where undergrads have to use it for their senior design projects, they will be able to use it correctly without knowing the exact details and without having to search through all of these possible footguns of ways they could be implementing something wrong. And also, what I found when I was implementing this is that even though all of these planners I'm working with are sampling based and require graphs, you would think that it would be hard to implement this in Rust, where we have strict ownership rules and we can't just have pointers pointing everywhere. And my opinion is actually, no, it's not that hard. In OMPL or other planning frameworks, you might often encounter a tree-like structure like this, where I have pointer soup, where every node in my tree has a pointer to its parent, and I'm constantly like juggling these pointers around. And this would be impossible to translate into Rust. But we can also do this with a sort of flywheel-based vector batch approach, where everything lives in this giant array that I then manipulate using indices instead of pointers. And in practice, this level of array backing is much more performant because I'm not allocating and deallocating all the time, and it's much better for my branch predictor, and it's much better for my cache alignment. So this is all very nice. And additionally, in this framework, we were able to find that we can get very good planning times. So I implemented the same SIMD accelerated planner that I talked about at the very beginning of this talk inside of the Rust framework, and we find that we were able to generate the same kind of performance results with planning times on the order of 100 microseconds, which is really, really nice. So to summarize from this talk, the proposed data structure that we talked about in the first half, the collision affording point tree, massively accelerates point cloud collision checking and makes basically all of your motion planning algorithms, whichever you want, faster in dynamic and perceived environments. And in the second half of the talk, I sort of discussed new ways of thinking about how we build these motion planning frameworks and how we get them to run efficiently. The QR code on the right is the link to the Rust implementation of the data structure that I proposed today. Unfortunately, the motion planning framework is not yet finished or ready for publication. I'm hoping to get it out soon, though. Thank you all for listening. I am very happy to take your questions. Thank you very much.
All right, thanks for the talk. Any questions? Oh, all right. I'll have a question for you. Okay, yeah.
No, you go first.
Oh, that's yeah.
So yeah, that's pretty amazing. Like parallelizing and linearizing algorithms is really the future of like robotics and putting that into real applications. My question is about like what type of silicon did you implement it with? Did you try on GPU, on CPU, AVX512? Which one was the best from your experience?
So so to clarify, which architecture did I implement this on? Run it?
Yeah, exactly.
Okay.
So you could run that on GPU too. GPU is like a huge simply machine, right?
Yes. So our benchmarks were run on a CPU. I think it was doing x86 with AVX2. This approach would certainly work on a GPU. That is sort of like one of my projects that I've been kicking the can on for a while, but I'll get around to it eventually. And I think it would be really interesting to explore. So I would very much like to do this on a GPU when I get the time.
Okay, good, thank you.
Any other questions? I think we have 5 more minutes. Yeah.
Do you know about Dora Rust?
Dora RS.
Yes, Dora Rust.
So
So how we compare?
so I'm not an expert. The Dora RS expert is right there. My understanding, and you can totally correct me if I'm wrong, is that Dora RS is more of a communication and pipelining framework. So it's a tool for moving data around. While the motion planning framework I talked about in this talk is really for a specific problem, specifically finding a collision-free path from point A to point B. So we're solving different kinds of problems.
Any other questions? Yes.
So on your slide with, when you were talking about the, getting away from pointer trees and going to dynamically sized arrays, haven't you just basically invented your own allocator at that point?
Have I just implemented my own allocator? Yes, that is entirely correct. I suppose it's slightly better since you get a little bit of type safety on top of that, but in practice, it's the same result. If you actually look at the code that gets generated, usually loading a pointer with an offset is about the same speed as loading a pointer directly, so there's not even much of a performance loss. But in short, yeah, you're implementing your own allocator, but it's with a little bit more safety rails on.
Okay. Because I was thinking like, does that circumvent type checking maybe a little bit?
Yes-ish, no-ish. I would say it's more useful than raw pointers, because with a raw pointer, you don't know where it's going at all, and you don't know about the initialization status. In this case, I was still able to get access to the same inbounds checking that you would get for an ordinary approach. Unfortunately, the Rust type system is not strong enough to capture that this index came from this index, this instance of that data structure. But if you could capture that, then you could literally make it impossible to use it wrong. Currently, you can just use like a new type to say you can't use it anywhere else. But for now, we're stuck with a good enough approach.
And did you ever consider using smart pointers?
In C++, or in Rust, or both.
Rust, like Box?
They get used in some places. For the planner specifically, it's more efficient to have it all in one contiguous layout because you want to avoid allocating as much as you can. But in some of my other stuff, yeah, I throw RC all over the place.
All right, thank you.
Thank you.
Yeah, thanks for the talk. Actually, this slide is perfect because I guess in C++ here you could also shoot yourself in the foot, whereas in Rust you can't. But that only holds true if you're not using unsafe, right?
Yes.
So I was wondering how much of your code is unsafe, and if so, like, is it completely safe? Or if you have used unsafe, what are kind of the things you need to do in unsafe, and why can't you get around that? And is there like a path forward? For example, I think for the index problem that you mentioned, there are ongoing discussions to say that a type like encode in the type that your index doesn't have to be checked because it can only be within the range, stuff like that. So if you can talk about like what parts are unsafe and why, that would be great.
Okay, so how do we handle safety? So I have a long answer to this. I'll try to cover what I can. So for the motion planning framework, there is very little in the way of unsafe code. I found that bounce checks don't really count for that much performance loss. The only bit of unsafe that I can think of on the top of my head is a little bit of stuff with converting pointers between direct an array and into my sort of compile time vector type. And that's very easy to verify the correctness of. In the data structure work, the collision avoiding point tree work, we do a lot of unsafe code because there is no way to safely use SIMD gather instructions right now in Rust, which is unfortunate, but for now it's unsafe, but it's much easier, in my opinion, to reason locally about a small unsafe section than it is to reason globally as you would in most other languages. And the second was about new types. So for index types, currently I am just going with no real wrappers on my indexes for nodes. But if we had better dependent types, I would say it would be a real boon for making this look more correct and making this harder to misuse. But I would say it's a nice to have, but I don't think it's super important. Make sense? Okay.
I think we are right on time. Let's get a cover. And I think our next speaker is. So this, and I actually didn't use it. I actually didn't use this. Because this is not the possibility. Test. You share the screen. I don't think you share the screen. I don't think you share the screen. Is it? You don't know, you can choose. Yeah. Are we there? Yes, wonderful.
There it is. Thank you.
Okay, so our next speaker is Rory Moran. He's a PhD student at the Queen's University of Belfast. His research mostly focusing on nonlinear and stochastic model predictive control for robotic system. And Rory is actually undersupervised by Dr. Pantelis Sopasakis. Okay, and their lab is actually also focusing on like numerical optimizations and also stochastic model prediction, stochastic MPC. So today he's going to give us a talk on the library, Rust library of optimization engines for in general like MPC and also code generations, right?
Correct.
So yeah, so without further ado, the floor is yours. Yeah.
Thank you very much. Yeah, my name is Rory. I'm from Queen's University Belfast, which is a university in the north of Ireland. So it was a bit of a long haul to get here. But we're here to talk about the software optimization engine, or just open for short, which at the low level is a Rust library, but you don't actually need to know any Rust to be able to use it. It was created by Dr. Supazaki a couple of years ago, and the two of us now maintain it. So for those who haven't been introduced to optimization, it is basically decision making. So if you had two projects you were working on, and you had a certain amount of time to do them in, you would devise a cost function of those to say one is twice as important as the other, maybe, which means you would spend twice as much time on it, and then that solution is your optimal answer. So you can work that out in your head. I understand that, but there are some problems which you will see need a computer to solve them. And that is an iterative process, which is quite difficult for the computer and can take a lot of time. But if you write your underlying code in Rust, then it's going to be very fast. So we're going to start with why open, because obviously it's not the only software of its kind. Then we'll look at some problem types you can use for open, or you can use open for, then some applications of these problem types. Then to the mic, sorry. Is that any better? I don't think it's on.
It's not on.
I can just
Okay,
talk louder.
that's fine. Test. Okay. Test. Okay, now works.
Test 1, 2, 3, 4. Yeah,
Yeah, it's working.
that's fine. What did I do? Okay, so we'll look at some applications for these problem types, then some results, some success stories. Then we'll look a bit under the hood at the actual Rust library that does the solving, and finally some code examples, but they will not be in Rust entirely, because open takes the design or the problem from any language that you can call a TCP interface from. So I would write most of them in Python or C++. And we have builder patterns so that you don't, you can just make your cost function, your constraints, and then ask open to make you a Rust optimizer, which uses a Rust solver engine. And then you can call it from your Python or your C++, or if you really want to do, you could call it from Rust. So what makes a problem suitable for open? If you're using an embedded device, because you can cross-compile your optimizer for your device. The underlying optimization algorithm is called PANOP, which all the numerical routines are written in Rust, which means it's fast, accurate, and safe, with very good convergence properties. Because you don't have to use Rust, it's quite user-friendly. You don't have to learn another language. We have well documented it, and it's open source. So not only is it free, but if you wanted to add something to it, then you could. So I'm gonna have to get into a bit of maths here. Optimization is full of maths. And generally the type of problem we try to solve with open has the form of the top right here, where you're trying to solve a problem with decision variables U and set parameters P, where you're trying to minimize over your decision variables a smooth cost function F, subject to the decision variables being within a set, and smooth functions F1 being in a set, and smooth functions F2 being inequality constraint. You can generally, most constraints that you want to cast, you can cast into either F1 or F2, but we use the augmented Lagrangian method for F1, and that generally leads to better performance of the solver and lower runtimes than the quadratic penalty method that's used for F2. And it's nice knowing that even if your problem is non-convex, non-linear, constrained, and all the way up to medium size, then you can still use open and it will run perfectly. So what are some applications? I'm hoping those blue dots showed up. Yeah. Maybe you wanted to do non-linear least squares where you have a line such as the green dashed line, and you wanted to optimize a best line fit to that. So if you don't actually know what the green dashed line is, you just have very noisy measurements, which are your blue dots on the graph, then you can formulate a problem where your decision variables u are the u0, u1, and u2 in your exponential function. Then your x and y of each of your noisy data points are the x and y sets here. And we've just added some inactive constraints, but you don't know they're inactive until you solve this problem. And you get the red line as your answer. Your u0, u1, and u2 leads to this red line, which is the best line of your noisy data points and will be a close enough approximation of your true model. Another one that I would be more involved with is a problem of model predictive control. So for those of you who have never heard of it, it is like playing chess. You look a certain number of steps into the future and you plan an action for each step, and then you apply your first action, and then you scrap everything, take that first action, and then start all over again. So it leads to quite big problems like this. And on the left, you can see obstacle avoidance, where the blue dots are your vehicle position, and it is moving from the bottom left up to the top right while avoiding this ball in the middle. And so at each blue dot, you'll calculate so many steps into the future, what to do, and then you'll apply that first control action, your throttle and your steering, and then you'll bin it and solve a problem at the next blue dot, and over again until you get to the end. So you have a problem of decision variables u, which are your control actions like throttle and steering, and your vehicle states z, which is your position, and you feed the problem z0, which is where you are now, zref, which is where you want to be, and r, which is the size of the ball at the origin. Then you minimize over the decision variables u and your vehicle states z, a certain number, n, number of stage costs, which is the number of steps you're looking into, you're planning for into the future. And then you generally have a terminal stage cost, which is saying when I am finished, I want a big cost on being wrong at the end, which makes a little more sense in a couple of lines. So we've set Z0 to be the bottom left, Zref to be the target at the top right. We have some vehicle dynamics, which we're not going to get into here, which is just a function f of our state and control actions. And then we have our stage cost function. You get to decide what this is, but for moving vehicles around, this is the general one. The first Q norm constraint is a penalty on your state being away from where you want it to be. And the second R norm on U is penalizing having large control actions. So you don't want to put the throttle to the floor or turn around in circles. And then at the end, you want QN to be much bigger and say large penalty if I haven't made it to my target by the end of my planning stages. A couple of small things are that your Q matrices have to be positive semi-definite and your R matrices have to be positive definite, just so that your problem can converge. And then you'll have some max between this and this type of constraint for each stage, so that all of the states along your planning path do not go within a certain distance of the origin, so you stay outside the ball. So if model predictive control is planning several steps into the future, its complement for estimation is looking several steps into the past and trying to determine an estimate of your state at the time is now. So here we have a problem where the decision variables are your estimated state X, and the Y, your parameters are the measurements Y that you've taken up to now. And you're minimizing over several steps in the past another Q norm constraint, which you can see is the process noise WT, and you're also there's also the measurement noise VT, and your Q and R have the same constraints on them. So you can see on this graph we have a three-dimensional state that is moving around, and if you see at the start bottom left tail, the estimated state is quite far away from the actual state, but by the time you make it to the top left tail, these are much closer together because you have more measurements behind you that give you a better estimation of your current state. So what are some success stories with these problems in Open? We have benchmarked it against the state-of-the-art solvers that use interior point or sequential quadratic programming methods. However, these methods use quite heavyweight inner iterations, so they are 1 to 2 orders of magnitude slower than Open. And you can see in the bottom here, this is against IPOpt, which is an interior point solver, and is also free, but you can see that Open is up to or more than an order of magnitude faster. And you can see that N being the size of the problem, as the problem gets bigger, the solve times increased the same amount for both solvers. Here we have a quadcopter that's using nonlinear MPC to avoid the cylinder in the middle, and it's just moving from point to point. This is on an Eon upboard, and anyone who's worked with quadcopters knows that there's pretty tight runtime requirements to be able to fly, so this proves that Open can solve things very quickly. Here we have a portion of a simulation where the little yellow thing is a scale race car, and this is in Gazebo's simulator, where the race car has to minimize its lap time while staying within the boundaries of the track and maneuvering around the obstacles or the other cars on the track. And most recently is a track loader, which is a small bulldozer, and we've used hierarchical nonlinear MPC for obstacle avoidance, for avoiding an obstacle which has a fun name called a super ellipsoid. And we did this on an NVIDIA Jetson TX2 with a simple unicycle model, and again, for safety, you had to solve these problems faster than 10 Hertz. So your 100 milliseconds is the absolute hard limit on these solve times. So what is under the hood? We have this workflow. I'd like to iterate that all numerical routines are written in Rust, even if Python or C++ is mentioned. And you can cross-compile these optimizers for embedded devices. So you would start with the maths that I talked about in previous slides, and that would become your problem. So you have your cost function and your constraints, decision variables and parameters. Then you would put this into a builder with metadata like what you're going to call it and who you are. But then you have more important things like the builder config, which is where you want the optimizer to be built. The build mode, there's debug and release. So if you want something to compile, you want the optimizer to be built quickly while you're trying to fine tune it, but you don't really care about how quickly it's solving the problem afterwards, then you would use debug mode. And then if you wanted a longer time to build the optimizer, but very, very fast runtimes, you would use the release mode. And then you have some solver configurations like to what tolerance do you want Open to solve it to? What's the max constraint violation you'll allow? How many iterations are you happy with? And what's the max time duration you have? And Open puts that all into a box and builds you a Rust optimizer that you can call from kind of any TCP interface. We would normally use Python or C++. And everything that you would do as the user doesn't have to be done in Rust, but it can be. So whenever you build your optimizer, it generates a Rust library, which is just one file and contains all of the functions you would need to run this optimizer or call it. However, the current drawback for using a Rust only implementation is that you have to give the cost function and the cost function gradient, which would usually be computed for you. So it's a lot easier to use Python or C++. So as an example, we have the Rosenbrock function, which is a standard performance test for any non-convex optimizer. And you can see for the two-dimensional case, we have a function of two decision variables, x and y, and two parameters, a and b. And if you look at the MATLAB surf plot on the left, you'll see that there is a long parabolic shaped flat valley inside here. And while it is very trivial to find the valley, it is incredibly difficult to find the global minimum because it's so flat. It has other names. It's also called the valley function or the banana function. And it doesn't have to be two-dimensional. You can have any number of decision variables. Here we just have the two, x and y. So if we take it up to having 5 decision variables, we have a problem that we're trying to minimize over our decision variables u with parameters a and b, and you're minimizing the cost function, which because it's a test function, we already have it inside Open and you can just call the function instead of building it yourself. Then we're going to look at nu is equal to 5. So for this case, we're going to have a global minimum at all ones, 1, 1, 1, 1, 1. But there is also a local minimum at -1, 1, 1, 1, 1, which we don't want to find. We want to know the global minimum. So we have built it in debug mode and set it to a tolerance of 10 to the -5. And then we called the optimizer by giving it the parameters a and b and asking what is the answer. So I was hoping this would just come up. Ooh. is PyCharm. I'm not sure if everyone's knows about it, but it's just a good IDE for Python. And here we have the same code, pretty much, calling the Rosenbrock function for 5 decision variables. And this first part is for building the optimizer, just a couple of lines of code. And this next part is calling the optimizer with the parameters that you give it. And if we run it, then you will see the verbose output of building the optimizer. I can't really read it from here, but till about here, it's all building the optimizer and putting it in a folder. And then the next part is building the TCP interface, connecting to it, calling it, and then getting the answer. I'm hoping that's the right one. I can't really see it, but we can go back to this and a lot easier for Bird. You can see inside my optimizers, which is where I've told it to put the optimizer. You can see there's one called Rosenbrock. And if you go into source, then you will find a lib.rs file, and in here are all the functions that you need to call this from Rust. And it's just one file. And it always makes it so you don't actually have to tell it what to do. But again, for the moment, you have to provide the cost function and its gradient, which can be a real problem. We have much more examples. So if we go to the landing page of Open, I'm hoping it comes up. Then you can go to GitHub, and in the examples, we have created the Rosenbrock example, but completely in Rust. So if you are planning to try and do it all in Rust, then this would be a good starting place. But you can see that while you have the cost function, you also have to provide its gradient. If you can, it's all good. If you can't, use Python. We also have, from the landing page, you can go to the docs, and there's an installation page where it'll just walk you through easy installation. Then the last thing I'd like to go to is the examples, where we have what I showed earlier about the NPC for a vehicle avoiding a ball. It talks you through the dynamics of the vehicle, how to build cost function, how to build the optimizer. But what the nice thing about it, which not all optimizers can do, by the way, is that it is a parametric optimizer, which means when you're doing model predictive control and you get to this point, because you are providing the target point as a reference and a parameter, it means that while it's moving, you can also adjust your targets. You don't have to build a new optimizer for every time you want to change where you're going. So you can change your reference target, but also use your previous answer and move it move it around slightly where you remove the control action you've just used, bin it and repeat the last one, and then provide that to the solver, and it takes that as an initial guess. And since it's a pretty close answer, your next solve time will be orders of magnitude faster. So hopefully you are not reeling at all the maths, and thank you very much for your attention. Do you have any questions?
Questions? All right, yeah, go ahead.
Hey, thanks for the talk. So how does this compare to Akados, if you're familiar? Because I think Akados does basically the same with C. Any huge differences there, also in speeds? Because if you're doing real-time MPC, most of the time you're not using IP-opt, you're just using Akados, for example.
I don't think there is much of a difference, and I would say that's just a competitor.
Okay. Have you benchmarked against them?
As far as I'm aware, there's more benchmarking on the website, but I haven't seen one with Akados. We'll have to have a look at it.
Okay, cool, thanks.
Any other questions? Yeah.
Thank you for the talk. I have one question because you just mentioned that right now, we do need to code the gradients in order to run pipeline. There's an auto differentiable capabilities gonna later on be upstream into the ROS toolchain. I think it's in the process. Do you think it is easy to adopt that feature in the project so that people don't decode the gradients, or you actually see some difficulty?
That is a great question, because no, I don't see much difficulty at all, because we have already done it. We published a paper a year or two ago called GradGen, and it is a Rust implementation of Casati's auto differentiation, so that we're planning to migrate from Casati's automatic differentiation to get the gradient, and instead use GradGen and Rust to compute it that way.
Okay, thank you.
All right. Any other questions? Right, if not, let's go. I think we are going to a coffee break for 15 minutes, and then we'll come back here at 3:45.
So I think if you already found, I do think that you're right. Yeah, true. Yeah, wrong. Yeah. Well, I mean. Well, I mean, I think like they use Python. Yeah. And so this is what, and the thing is like coding are like pretty cool. And for example, if you, I mean, depending on how very like, but let's say you don't have like a whole team, like especially when you work on MFI or like 40 might be very to run back to the the thing is like a very cool project and to or BLM or maybe and yeah and so if you want to have like very good performance, like very fast, right, just like
like this is what wrong.
Yeah.
If you first very heavy and and maybe I don't know if it's yeah, we do. Yeah, right. Well, the thing is, if you're trying to only there's a good chance that you want to have let's say you want to have very fast pipeline. You should make sure that you where you collect the data and will get started and so this is well also do our requirement for well to make the focus and to have a very efficient pipeline for pipeline. Any way that you can do and keep it good at but it's the truth be told, I think the white is still very young, and I think yeah, if you compare to people well, people on both, I think we're not there yet. Also, yeah, but also there's one thing. I think like it's really right. Well, that's also something very well. We go out and do very hard on to make it work. Like not very good, you know, maybe we could kind of better. Kind of like where like it might be. Well, you no, I think that's rough. Right. Yeah, I mean, I think the drive is the tricky thing when you really trying to make something that can work on multiple levels, so not just Rust, but and so if you compare to code, for example, like we had this morning, like you can have all C++, we can have a lot more optimization if you just stick in one method, right? So the like people also are less, yeah. But then like there's like. Yeah, to be honest, and like there's a lot of very good product types in my opinion, right? And like I think for a lot of people they don't have the team to just put everything to us or everything. Or just work with by binding. So and if it's the case, we think like Rock 2, it is a binding between Python and whatever it is, but well, this is pretty powerful. And it's not necessarily obvious as well, because there's a lot of like tricky things about Python, and this is where the one let's say afterwards. Thanks. Yeah. Sorry. I think no, I didn't get it, but maybe it's because I just put it. I didn't get the thing. The next year is again. And I hope that next year I have to go back and just be to like all the time. Go like all like that.
I missed the presentation. I was at the robotic software architecture. It also like they were very focused on ROS2, level abstraction. ROS2 control. Our team uses ROS2 control a lot. So yeah, I was trying to I'm kind of curious if there's a place for like ROS2 control and Rust, but kind of a lot of bindings.
Yeah, I think there is some working on this, but that's the thing, right? So I think I'm rough, full rough, right? That's also something that I want, like the harder to do around the application, where there are people want to do it. And
right. The binding from Rust to Python is much easier, than C++ binding. Python is the nature of it, or it's more informative as well, and just to get the other benefits of Rust. I don't actually know how good C++ binding. I would imagine that they're not that much fun because they get super. But yeah, the Rust Python binding I would say is pretty good. There's still some Rust in the second now. But I think it's pretty good.
it's not perfect. But it's bad, but I think we will get a lot of this. And by that, I mean like all the ML platform. So I mean, I try to do a lot of things to just break everything well. Okay, yeah, okay. Okay, I think well, I'm not actually the biggest advantages, but also something that's really pushing is this idea of generating when it's been looked at. So that's what it wants to do. When you send an image or when you have something data, like the layout, like every data is going to get the rate of the time. But it could work very well with FTP or like FTP or like int or whatever. And so we try at the right to have generating all the time. And that it will be fine in the rest as well. I would imagine that you can work around generic basically verify. Yeah. But I think we're going to see some necessary with I think we're like so we have all like basically like we are our own like but we use them to do the time. Okay. Yeah. And, one thing that I'm working a lot on is because it's not fish, just if you have a lot of like human stream, fishing test data. Yeah. And this is also where I think yeah, I'm using AV1. Yeah. The good thing with AV1 is that you can have like pretty good sort of fit. So you can go like that thing. So you can basically what you create a minute. You have 12 bits to the roles. And then you have a very way instead of doing something in the don't really know what they are. So and we really try to make this into the one the way that people that but it's also very tough because like the picture set from drop is very big. Yeah, you compete it. Yeah. So but yeah, well I think it's see the other pictures. Different, yeah. I think like my video space is not very important. I think there's gonna be other people coming a lot. I think one of my biggest like thing I'm focused at the moment is so like something like rock. If that you are like yeah, you think like I'm frankly not very comfortable and so it's fine myself, but I really do feel like to keep you all the like it's gonna be more and more like a GPU. And so I'm just seeing all these stuff like merging different like no together like maybe more involved and name it. Yeah, keep roll factors, yeah, roll center and then yeah, very well. And I feel like the looking at it's actually very well like the take care of the very base and model so then but then that's why like but then like good thing is that it's like actually big model are terrible at visual one. And so that's why That kind of safety. Yeah, it's the point of found it's very helpful. Or just like a test camera really helps you on getting things out. Like basically you can do something on the 3D and then like you know the 3D a lot easier to go to the AI. Then like so we think about but yeah, I would say the difference might be like you know get make a like NVIDIA spending super cash on like interest or end up being like we're waiting on it. And that
There's so many companies that are building off that hype.
yeah. So what do you work on? Any of those?
I work at ICRA2025. Yeah. Can't say something. Yeah, I'm looking for most of the focus on texture manipulation, right? And AI model around them. Also evaluating different robotics. The carbon on the dip, which makes them match, and then like our so kind of on the yeah, so when we first have our like very
How you let go? Yeah.
so their EM on it, so they're like academic.
Time shift is starting to catch up with me.
Building our more.
I was in conference last week.
Extremely dexterous, like also within the whole.
Oh, wow. Where?
Yeah.
With animes.
Okay.
Okay. Really starting time.
Yeah, I'm still. It's quite.
Either.
Yeah, oh yeah, actually.
I was prepared for
Like seven cells.
Were you also organizing anything there or just?
Yeah. Another
My phone, how much you can just slide and lay that so that you wear on.
Actually, just for so we're organizing a workshop there. Yeah. Well, and back to back,
Like in-house.
and some of our colleagues fly over
So
Europe.
like
Yep.
yeah.
It was literally like feeling a lot of busy like the first 2 days.
But I think do you guys have work on like
So I guess it started catching back now.
Yeah.
I think it's good. I think like
Well, and I.
Yeah, it limits you in verification, but still.
3:30 this morning, something. So with the rest of the company being still working,
Yeah.
they're working in there, you're like, I'm wide awake at 3:30 this morning, and then I make the mistake, I get on Slack, right, and I look at Slack, and so like, people are discussing stuff, and I'm like, oh, I kind of wanna like respond, I'm like, no, this is waking me up more, I need like, close the laptop, go back to bed.
But where is 9 AM Europe?
3 and here is. Yeah, 9.
So they
Yeah,
just.
They're just starting
Starting
they're
today,
just
right?
posting their updates, and I mean, so we just had a full team meetup last week, so there's a lot of like, we're kind of like getting into this week and kicking off a new cycle of planning and sort of the next month or two.
like to the point where I'm like, well, okay, this.
Yeah. So those of my European colleagues who all feel like the jet lag is actually catching up. Last week was the same thing. Like, European colleagues like busy in the first few days.
Yeah.
But I'm getting there.
Let me see if I can contact them.
Yeah,
And
yeah.
I
I think
the
Danny is right. Is there, right? Hi, Danny. Can you hear us?
I'm here. Yep.
I don't think the audio is one.
you mean the audio of the laptop?
It's the audio from our side.
Okay, 1 second. Oh, no, I know why. Thing. Yeah, there you go. Hi, Danny. Can you say something again?
Yeah, is it working?
Perfect.
working.
Yes, now it's working.
Awesome.
Awesome. Right. I think we can get started.
Yep.
Right.
That's really cool.
All right. Hi there.
Okay.
So, hello everyone. So we are now going for the last keynote talk of today's workshop, and then we will go into the final panel discussions about the Rust programming for robotics in academia and also industry connections. So the last keynote speaker is Danny Rakita. He's a professor at Yale University, and he has done some very amazing like open source work for planning and learning optimizations using Rust for robotics research. And today he's going to talk about his work in this domain. So I think it's going to be a very fun talk. So Danny, yes, the floor is yours.
Awesome. Thank you so much. Before I jump into the rest of the talk, I wanted to give this link to some resources and code snippet that will be relevant throughout the talk. I hope this is interactive. I have some like live coding parts later in the talk. So yeah, feel free to take a moment to go to this page if you want to follow along. Okay.
We got some folks scanning on the.
Yep. Okay. Yeah. I'll wait a few seconds. Sounds great.
All got it? All right, cool. You can go
Awesome.
ahead. Yes. Yes.
Great. Okay. So yeah, so I run the Apollo Lab at Yale, where I'm an assistant professor. So we're doing a lot of work at the intersection of planning, learning, and optimization, hoping to apply these in real world spaces of, home care, manufacturing, healthcare, things like that. So here's a structure for the talk. So I first want to go through kind of like how I stumbled upon Rust for robotics several years ago. So let me just jump right into that. So I would say that about the first half of my PhD, I was just using Python. It felt like the default option to land on. Everybody seemed to be using that, using Rust code to, glue everything together. And one work that I want to highlight, during this time was RelaxIK. So we presented this at RSS in 2018. So the goal here was to make, accurate motion while still being feasible, avoiding self-collisions all in real time. And comparing this to other work around that time. Again, we're aiming for this kind of smooth, accurate, and feasible motion all on the fly. And thinking about the runtime of this. Oh, actually, before that, let me just bring up, what this repository looked like, at least at the time. Well, it's actually accumulated quite a number of users over the past few years. So if we just look at the original code here again, it's just that, standard Python code all tied together, in a very haphazard way. And if we think about the runtime of this, the first version of this solver was running about like 30 to 70 hertz, which if you're not working in this area, this is actually very slow, much slower than like the runtime frequency of, basically all robots that are available. And to really think about how this affects things downstream. So we did some work that directly used RelaxIK. Essentially the following summer, I was working at an internship at the Naval Research Lab in DC, and we wanted to apply this on bimanual robots for this bimanual control problem. So our result looked like this. Yeah, there are some cool inference steps going on in the background to like recognize, bimanual actions that are happening in real time and kind of filling the gaps in. But essentially the thing to focus on here is all the motion at the end of the day is being driven by RelaxIK, and at the time just purely in Python. And this bimanual robot being a 15 degree of freedom system here. This is more on the 30 hertz side of the range, and I would say over half the summer I spent trying to figure out like filtering algorithms, just ways of overcoming this like very slow optimization solver. So after that, I knew I wanted to push in a different direction. Python really wasn't interactive and fast enough. So I very briefly looked at the Julia programming language. When we re-implemented RelaxIK in Julia, we did get a pretty good speed up, so about 150 to 200 hertz. The biggest holdup there was actually as I implemented a larger and larger library, the JIT compilation speed was just far too slow. So even like single line changes at the time took like minutes to recompile, so that just really wasn't feasible for especially the workflow I was going for. So after that, I just took the plunge and went in a fully compiled direction. I considered C++, but I didn't want to go in that direction. I'm very happy I stumbled upon Rust at that time. Uh, prior to 2020, like right when I was trying this out, it really felt like I was kind of on an island in the robotics community, really getting started with Rust. It's very possible that many people in this workshop were also thinking about it at that time, but at least at that time it felt like I was more on my own. So very happy to see several years later, there's a workshop on this, so that's definitely great to see. So yeah, just to give a sense, so even this first try of RelaxIK, even at that time without a lot of experience, this was immediately faster than 1,000 hertz, which again, given the research goals I was going for, this is not just a convenient speed up. This is like an enabling technology difference. Just that level of speed up that we were getting. Given more experience and more tricks, we're actually able to get this closer to 5,000 hertz for a lot of applications, and possibly even faster. And I'll talk about some things that get it close to that, but yeah, just to give a sense of what the timeline looked like for that. And also to give a pointer to our current RelaxIK repository. So still, lots of people stumbling upon this and using it. It's still being supported. We have different versions of it now that have like collision avoidance and ranged goals. And yeah, so all the code now is just in Rust and pretty performant. So definitely feel free to try this out if you're looking for this kind of IK solver. Okay. So yeah, around here in the timeline, so end of 2022, I founded the Apollo Lab at Yale. So a lot of the story of this talk is going to be focused on the end part of this timeline. So just what we've been working on in Rust over the past couple of years in my group. So really hitting on that. But before moving on to that, I want to touch on, just the high level of, why Rust in an academic setting. Why did I land on that and really stick with that for a long time, even now? So as I said, this is very fast, the fastest compiled code that I've used. So that's really important for my area of research. Second, Cargo is really the best package manager I've ever used. It gives a lot of confidence in running an academic lab that I know I can pass the code off to my students or people in the research community. And I trust that the code is just going to run the same on different systems. And I can't say the same in terms of trust from other languages that I've tried. The parallelization is great. We do a lot of things with like parallel trajectory optimization. Just being able to wrap, like a Rayon parallel iterator is just, fantastic. So I actually don't believe that I program faster in Python or like a similar interpreted language. I know that's kind of like what people say and think, but I find that whenever I program in Python, I'm losing track of what type things are, and dealing with like dependency issues. I just feel like those similar things don't come up when I program in Rust, and I can really think and program pretty quickly. And also, several years into this process, I feel like the Rust compiler has really made me a better programmer. So it feels extremely strict at first, but now it's kind of my best friend in programming. It's really great. So okay. So moving on to, again, what we've been working on for the past couple of years. So kind of leaning into the name of my lab. So we're building the Apollo toolbox. So this should give a good sense of what we're aiming for here. So at a high level, the inputs to the toolbox are, a robot or environment, just as a URDF. And then also the corresponding meshes that go along with that robot or environment. These inputs are then pre-processed all in Rust code, and I'll show kind of what the pre-processed output looks like. Essentially, these are all what are called module files. So it breaks it down into a lot of collision information. It does like mesh decomposition, just tons of information about those things that can help at runtime. So to give a sense, on my computer, I just have like a folder with all these directories that have all this derived information. Again, all derived in Rust. But then the goal is to allow these module files to more easily plug into essentially all these front-end options. And really the end goal is to allow for all of this code to nicely plug into a lot of graphics front-end options. So to briefly touch on one part of this, not related to Rust, but what makes this structure really nice. So looking at the JavaScript part of this, using these module files, I can immediately load this into like a Three.js environment and get like a really nice sense of like what the pre-processed files are actually showing. So for example, I can move around the robot just to make sure that the kinematics are good. I can look at all the frames. I can also see the convex decomposition that came from the pre-processing, also visualizing that as convexification of spheres. So this has been like a really nice visualization tool and very shareable just in the browser. So that has been pretty convenient. So yeah, a lot of this talk, of course, is going to be focused on this connection between Apollo Rust and Apollo Bevy. I would say that we're still favoring this part of the library. It's still kind of like the center of everything. So really focusing on how to advance everything here. So next, I want to talk about how we're computing derivatives in the Apollo toolbox. I think this, builds on the last talk very nicely. I think there was some great conversation just thinking about derivatives in Rust. So just at a high level, thinking about where derivatives come up in practice. So if we have an optimization, I can go back here. Oftentimes we have formulations in robotics like this where we want to minimize some function with respect to some vector variable like x here. So in practice, this can look like this. So maybe x is our joint rotation values, like the sliders that are here. Maybe we have some transform gizmo. And as we move this around, we want our objective to be the robot following along with this transform gizmo. So essentially that's a minimization like at every moment here. And we actually see the values updating in the sliders. Of course, if we have a robot like this, we can have multiple transform gizmos, and then we just embed all of these goals into our single objective, maybe using like a weighted sum. And but yeah, same process, same formulation. This comes up all the time in robotics. And a general strategy, again, building nicely on the previous talk, is to slide downhill iteratively using derivative information. So I think the simplest version of this is something like gradient descent. but the most important thing to focus on here is that just gradients come up all the time here, and we want to use this to, you know, iteratively find better and better answers in these kind of function landscapes. So the question becomes, how do we compute these derivatives on the computer? So there are a few strategies for doing this. So first is finite differencing. So we can like perturb the inputs on all of its individual like dimensions using these one-hot vectors, and just seeing using like the limit definition of a function, how the function actually, you know, how the outputs differ, you know, under these perturbations. So this is great. This is easy to implement, but it's really slow, especially when a function has a lot of inputs. We can also do something called automatic differentiation. So essentially breaking down any computable function into its atomic pieces. So the idea is no matter how complex a function gets on the computer, it can always be broken down into like these primitive functions like sine, cosine, power. And as long as we know the derivatives of these primitive computations, we should, in theory, be able to build this up to the full derivative of the whole computation using the chain rule. So there are different ways of keeping track of the chain rule through this process. So we can either forward propagate what are called tangents using forward mode AD. So this is nice. This is now an exact derivative, so it's no longer an approximation. This is fast when a function has few inputs, which is nice. This is relatively easy to implement, though it's still more difficult than finite differencing. And this is slow when a function has many inputs. This is why this is like never ever used for something like a neural network. So reverse mode AD first builds what's called a computation graph or a Wengert tape on the forward pass, and then it backward propagates what's called adjoint information on a reverse pass. So again, this is going to be exact. This is fast when the function has few outputs, so nice for something like optimization. This is more difficult to implement than the other options, and it's slow when a function has many outputs. So the objectives that we were going for in the Apollo toolbox were we wanted really fast derivative computation, especially for robotics applications. A lot of derivative libraries now are tuned for like neural networks, but we wanted this specifically fast for robotics. We want it really easy to switch between derivative computation methods due to the many trade-offs involved. You know, some methods may be better for one function versus another. And we really wanted to take advantage of advanced programming features like SIMD, which in theory is, you know, available in Rust, but hasn't really been well integrated into things like automatic differentiation. So when I look at these objectives, I would actually say Julia does this pretty well. I think it's one of the stronger parts of the language. Again, it has other, you know, drawbacks, as I talked about before, but I think it's really good for derivatives. C++, I think it's debatable whether there's any individual library that achieves all this, particularly, you know, switching out derivative types really easily. And at least at the time that, you know, we were first thinking about this, this really wasn't available in Rust. Again, I think there is conversation going on about, you know, things like source code transformation working its way into like nightly Rust. So very, very interested to try that out going forward. And interested to see how many boxes, you know, that checks here. But again, at least at the time that we were looking at this for robotics, this wasn't easily available. So what we ended up making was the AD trait crate. This is now up on crates.io. Still very actively developing. I just pushed, you know, another version of this a day ago. But yeah, this is definitely ready to try and ready to go. And let me walk through what this implementation looks like. So the high-level idea, as the name implies, is to come up with a trait called AD, and that types that implement this trait should basically be a drop-in replacement for standard floating point numbers. So this is overloading based automatic differentiation. And it ends up being that traits are just perfect for this in Rust, since everything at the interface level can just feel like standard floating point numbers. And then the compiler can make sure that everything implements exactly what's needed in order for it to feel completely transparent. Another nice thing that we set up is standard F64 and F32 also implement the AD trait. So this is should be truly zero cost abstraction. So you're not really losing anything, you're only gaining. You can always recover just standard floating point operation through these functions. And then again, the idea is depending on what derivative method type you want, the method will be able to track the right information behind the scenes as it's going through all of these floating point operations. So let me pull up a programming environment here and just show what this looks like in practice and how we can actually use this. So hopefully everybody can see this. I can actually do this. Okay, so let's say we want to make a function. I'm just going to call this foo, and we want this to be differentiable. So we can say differentiable function trait. We want to implement this for foo. Load this in. And we only need to implement a few things here, so just give it like a standard name. Let's say our function is going to have 2 inputs and 1 output. We're not going to need this. And we can just deal with the inputs here exactly like they are floating point numbers. And we are good to go here. So now we can instantiate something called a function engine. So we're just going to put in a couple of instances of foo, and now we can just drop in exactly what derivative method type we want. And right out of the box, we can immediately get the derivatives of our function. So just with a few lines of code here, we can immediately get both the function output and the derivatives. So we have 2 outputs. Again, this is just a function output, and then this is our gradient. So how can we use this? So we can instantiate an optimizer. Actually, to couple really nicely with the last talk. So we do have like BFGS, and we have standard gradient descent with our own line searches, but we also do have options for the optimization or the open optimization library. So let me just put some lower bounds here, basically unbounded. And we can just optimize for this. So let's say maximum number of iterations 100, starting at this initial condition. And lastly, just give our function, our objective function as input. And again, just in a few lines of code here, we can get the optimized answer to this. Oops, this has to be loaded in. Yep. So this converged in 7 iterations to best possible answer. It slid downhill really easily there. Yeah, so I have another example in the resources provided for this talk. Feel free to look through that. But yeah, hopefully that gives the high level gist of what we're going for here. Oh, one thing I was going to comment on. So one of the really nice parts about this is we can, just as a drop-in replacement here, completely switch out how we're computing derivatives. So we're going from forward AD to reverse AD. We can also do finite differencing, as well as forward AD multi. So this is using SIMD operations for all of its computation. So this is doing 2 channels of tangent computation at once. And this, again, works as expected. So having something that's just a drop-in replacement, you can easily try out different derivative options, has been really, really nice. Okay, so the AD paper trade has been submitted to ICRA2025, looking at some applications in robotics already. The paper is available on arXiv already. One part about this that I want to point to right away is some of the results that we got comparing this to other libraries. So we tried this out on a benchmark function. Essentially, this just composes a bunch of sine and cosine functions. It's meant to resemble something like in a robotics application. And we tried this out in forward mode and reverse mode, using either these are like gradients and these are like Jacobians. So we see on the left, when we allow for SIMD optimization, this is actually faster, or it's among the fastest available, including Enzyme and Julia and AutoDiff and C++. And it also includes JAX and Python and other versions here. But we see that when it gets to 1,000 inputs to this function, we're actually the fastest that's available right now, or at least that we tried. In reverse mode, we're also among the fastest. Enzyme and Julia was a little bit faster for the gradient example, but we're about the same speed as AutoDiff and C++. And it looks like we were the second fastest for the full Jacobian. Okay. So yeah, definitely feel free to check out that paper, try out that code. Let me know if questions come up. I want to quickly touch on visualizations in the Apollo toolbox using Bevy. So again, just looking at this connection between the language layer and the graphics layer. So the objectives that we were going for, we really wanted like easy modular robot visualizations. We wanted high quality visuals. So if we want to go all the way to global illumination or ray tracing, that should be available if wanted. And importantly, we wanted graphic subroutines to be like in line with other robotics code, kind of like pushing against the standard like Frankenstein ROS code that sends everything to RViz or Gazebo or things like that. Unity, like just a lot of that code kind of living in different places. We really wanted this to be in line and feel like a part of the core library. So this definitely wasn't available in Rust, but I think all of these objectives, it's debatable to what extent they exist in even other commonly used languages. If people disagree with this, feel free to point things out to me. But at least from my perspective, there wasn't something that checked all these boxes in an obvious way. So just to very quickly show what this looks like on the Rust side. So I can get the resources. So essentially, you can think of this as all the modules that were outputted from the preprocessor. I can get a subdirectory. So this would just be like the UR5 robot. I can turn this into a chain that uses an algebra backend in Rust, And then just in one line of code, I can say Bevy display. And this will automatically pull up a whole window that's able to show this whole environment. So a really nice way to make sure that everything was like pre-processed correctly, visualizing different parts of the robot. Nice way to view kind of the convex hull of all the links or the convex decomposition. Yeah, we have lots of visualization options here. So yeah, good way to show this in just a few lines of code. Again, I have another example in the resources for this talk. In the interest of time, I'm not going to go through that one. But again, happy to go into this more offline or after the talk. So lastly, just want to wrap up with a very quick discussion. So just commenting on the current state of the Apollo toolbox. So this is still very much an active development. We're pushing on this every day if you look at the GitHub repo. So take a lot of this presentation as just a sneak preview for the bigger picture. I will say that 80 trade is ready to go today. So try it out, work it into your robotics code. Let me know if questions come up. I highly recommend trying it out if you're interested. And in general, stay tuned for updates, reach out. We're hard at work adding in new features for planning optimization dynamics. We want, a physics simulation in this Bevy environment with, the Apollo Toolbox backend. So definitely stay tuned for that. And just some, final thoughts before I wrap up. I think, having worked with Rust for a long time, I think the robotics community needs a lot more Rust in these programming stacks. I think a lot of code in the community is just kind of in disarray, having a hard time, figuring out all the errors and dependency issues that are coming up. I think Rust can help with a lot of that. So very excited to push out open source code and be a part of the conversation that can get this more out there. And lastly, again, as I alluded to before, I think this workshop is a great sign about the state of Rust in robotics. So thanks to the organizers for bringing this together and for the invite. It's been great to think about and talk about. So with that, thanks and happy to answer any questions.
Great. Thanks, Danny. Any questions? Oh, yeah, please, yes.
Hi, Danny. Thanks for the talk. This is super great talk. I originally want to put this question in the panel discussion, but I think I can ask it for now because I didn't see other question coming up. I definitely see that your lab has a successful story adopting Rust in an academia setup. Could you share something like what is something that not super nice? What kind of difficulty did you encounter while you are adopting Rust or like forcing students to take Rust in your lab? Could you share some of your story here?
That's a great question. I think what has been a point of friction is that students are generally coming in not knowing Rust. So maybe they've probably heard of it at this point. Maybe they've dabbled, in Rust programming in the past, but very few students have delved into it like in any deep way. So having like that initial conversation of like, hey, it will be great to pick up these new skills and this new programming language, and I think it's going to have pay dividends in the future for X, Y, and Z reason. There's a little bit of convincing because I think a lot of students want to stay in like either their Python bubble, working in, PyTorch or whatever. So there's a little bit of convincing that has to go along. I also think the story, at least in my lab where we do kind of learning and optimization and control and planning, it's not yet clear like the best ways to incorporate the so much PyTorch code that's out there with these lower level loops that we're working on. We're working on ways of kind of incorporating those better, or possibly even longer term, more learning, kind of living in Rust, from the get-go. But I think figuring out the best ways of putting that together is still an ongoing challenge and story.
Cool. All right. Any other questions? All right. All right. If no, let's give another round of applause for Danny.
Yep. Thanks.
So I think we are going to the panel sessions now. Yang, please. Oh.
So, thank you, Ray, for chairing most of the session today. I want everyone give a round of applause to Ray for chairing the sessions. Keep the entire presentation flowing. So now I think we're going to the second last session, which is a panel discussion. So the purpose of this panel discussion is that I want to facilitate a communication between industrial and academia labs. I want to see each other, talk to each other, like what are the things that you need, what are the things that you want, what are the things we can provide, and what are the things that we need to discuss. So for this session, I want to invite Jeremy on the stage again, and also Danny, who is still on the Zoom. I also would like to invite Clayton also on the stage, and I want to invite Haishan on the stage as well. Let's give a round of applause to the panelists. Test audio. Test audio. Danny, can you hear us?
Yep, I can hear you.
Yeah, if you want, you can also open your camera.
All right.
Yeah, sorry, we cannot get the camera set up to show you the panelists on the stage. So
No worries.
it's gonna start right now. I think the first question I want to ask is that I know there's quite a lot of folks also in this room are not familiar with Rust. I have been asked a lot of time that if I am a Python or C++ engineer, how can I transition to Rust? And I think that would be my first question. Is there anyone want to share something?
So I think the best way to start with Rust is really to think about performance, at least for me. And so if you ever run some Python code and you felt like it was really slow, especially if you do like some form of image processing, it's gonna be very common. But writing the code, the very same code in Rust will probably very blow you away from the performance you can get. And then you add Rayon, which give you for free multi-threading. And so you can use all the cores of your computer, and then you get maybe 12 to 20 times the performance that you get from the initial code. I think it's really something that will stick with you. And then if you do robotics, you probably want to have some low latency robots, right? Because everyone has probably seen a very laggy robot. It's never really fun to have. So I think this is probably performance will be my key advice on getting started with Rust.
I think I'm going to agree here. I originally got into Rust because of chess engines. And I got into Rust just so I could program faster code for those. And so having a project where you're very motivated about performance makes Rust a very easy sell and makes it very convincing for new people. With regards to actually learning the language, I think the best tools out there are really just the main documentation book and then sort of freestyling it from there. I generally trust that if you're learning Rust, you probably know one or two coding languages already. And so you can kind of figure things out as you go.
Yeah, and I guess for Python developers, in particular, I'm gonna shout out the Pyo3 library ecosystem. Again, right? I think if you've got a Python project that you're working on and there's some piece of code within that library that you're interested in optimizing, right? This is sort of a good strategy for pick that thing. You sort of follow the Pyo3 tutorials, get yourself set up so that you can call that function through to Rust, right? Don't worry about the full overhead of setting up the an entire from scratch Rust project, but this like building a little Rust module that you can call from your Python project and start to expand and grow from there. I found to be like a really nice strategy for not solving all of the problems that like that you eventually need to bootstrap a Rust project, but just like focusing again on that one compute kernel, one piece of something that you want to optimize.
Yeah, just to briefly add, I think to add onto what everybody said, I think just reiterating again how good like cargo is for the just dealing with different packages and crates in Rust. I think that alone, it has been a real game changer for the way that I just view programming and sharing code. So if you're on the fence, like both the speed and working with cargo, I think if you just try it out for a little bit, even on small scale projects, I think it's worth the few weeks of pain of dealing with the compiler and learning what is allowable and what's not allowable. If you just get through that time, I think most people who stick with it just really really love the language and keep going with it.
Cool. So the second question, it's actually not a question. I want to as I said, I want to facilitate communication between people. So I specifically chose 4 panelists for this reason. We have founder, we have people who has worked in the industry for a very long time. We have younger generation students, and also we have PI running the lab. So from each of your perspective, is there something that you want to talk or you want to ask other panelists from other perspective? Like, this is something I need. This is something I need help with. So maybe we can start from that. Is there anyone want to start?
If you want, I can start. I think it's like Rust is a very great tool, very great language programming. But I feel like maybe some people in the audience and myself included, sometimes it feels like it's a bit hard to use it to write papers and academic papers. By that I mean, because sometimes you can't just say, oh, I did a really good, I ported this library in Rust, and it's often not enough, right? Even though for us, it's a pretty big deal, right? Like, let's say you write Torch in Rust, very big congrats, it's very hard. But like a lot of people would not care, right? Because it's not really like academically say like valuable, right? Because at the end of the day, you just ported something, right? And I think for me, it kind of my undergoing question and how do the audience feel about this is like, how can we make Rust more successful in the academic settings? When you have to deal with the borrow checker, you have to deal with a lot of things, you have to learn the language, and I feel like for a lot of people, it's kind of a deal breaker to do academic research. What do you guys think?
I think that is sort of the same set of problems I've been thinking about as well. I'm probably like most of the people in this room, and that I'm interested in these software engineering type problems where a lot of the algorithms might be more familiar, but the implementation details matter a lot too. And especially as an academic, it's very hard to come up with a way of selling the fact that I was very clever about this implementation and I got a 5x speed up, but so what? So what I think is I would like to hear about from others is, especially for academics, how do you present your very engineering heavy work as something that is still sort of a novel researchy contribution?
Let's see. Yeah. I think I'm just trying to think of like places that like that rerun really like intersects with academia, and one of the sort of the open sort of open questions I have like has to do with like the primitives of visualization, I guess. I feel like for the sort of like the classic the meshes and transforms and all all of this stuff is sort of like relatively like easy for us to visualize and think about. I don't think that gets us all the way to solving all of the needs of academia. And I see this being sort of a hard uphill battle for Rerun to fight here, where you like, we're good at visualizing things up until the point where our visualization primitives don't match the primitives that sort of like are being pushing the bleeding edge there. So I'd love to have just more of a conversation about like what are the future looking primitives, what are the things that we need to be thinking about in order to sort of have our visualizer be able to visualize the kinds of data that new algorithm development and new sort of approaches to robotics are going to require.
Yeah, just add on Jeremy's opinion. This is something that not only a trouble for Rerun. I think this is a issue for a lot of industrial company. I think they really want to help academia, but academia people didn't speak up enough. Like I think there's both sides want to communicate, but I think we do want to figure out a way to facilitate more communication between industry and academia. Daniel, do you want to add on something?
Yeah, I think I really want to continue to get a sense of what people's hesitation is in starting with Rust. So I think this is already a good start to that conversation. I also want to get a sense of you know, where people are at either with working with Rust or not working with Rust, and just like with how this fits in with the rest of like the standard like ROS stack of robotics, because it's gone through so many evolutions over the past 5-10 years, and a lot of it has been one step forward, two steps back in a lot of ways. And for me, I have purposefully kind of stayed on the sidelines of that. I'm like, okay, until the dust settles, I'm just gonna stay over in Rust world and just write very lightweight wrappers, you know, for ROS whenever necessary, but just kind of stay out of the fray until, you know, we have to get involved with ROS code to better integrate things. So I'm curious through some of these conversations, both through the workshop or afterwards, like where are people at with that? What are the pain points related to that? And are there ways that we can all come together to fix some of the pain points?
Thank you, Danny. I'm wondering, I think this is a question. I think Danny actually raised a question for the audience in the workshop right now. If anyone wants to comment on that or want to contribute to this panel, feel free to go to the microphone, tell us like what are the stuff that's like blocking you, or what's the stuff like troubling you while you may be thinking adopting Rust in your pipeline. Is there anyone want to comment? Yeah, go ahead.
There's someone in the back as well.
Oh, yeah. You wanna, yeah, you can start first. Okay. Yeah.
I saw like one few articles on Rust, and then I explored that last year. And the thing that I realized that we need the software infrastructure around like, you know, when I go for a new sensor, I'm pretty much aware that somebody's writing an ROS plugin for that. So that is what keeps me away from going away from the like the whole setup for ROS. And I know that Python is slow, but still, like Python and the ROS stuff, they have like so many active developers developing the community is so good that it's very easy to, you know, adapt new sensors and all without worrying about the underlying details. So how my question is how good the Rust community is in adapting new libraries and things for the sensors.
Thank you for the question.
Yeah, I think probably I'll be the best person to answer this question. So I agree that Rust, you know, there's a lot of community development, and like the thing, I think it's people might think that Rust is not yet mature for sensors and things like that, but it's actually not very true. I would say the thing is like basically you have a finite ways to communicate with the sensor. For example, you have serial port over USB, you have Ethernet cables. And basically, if you have a good specification sheet, it's actually very easy to use procedural macro in Rust to just create the bindings to this very sensor. And so you don't actually need to have, and some of the time, so I'm working with people from Robotics, which has been acquired by Hugging Face. And basically what we do is we just put some specification sheet of a sensor over ChatGPT. It writes for us. It writes for us some procedural macro in Rust, and most of the time it's even better than the manufacturer itself, because like you have all the guarantees in Rust over the C++ or even worse the Python code that has been written by the manufacturers, which most of the time, or like the community developers, most of the time have tried very little effort to make the code very good, right? And so, but we can do a lot with procedural macros in terms of verification, validation, type safety, and so I would say that yes, the ecosystem for hardware sensors is not there yet, right? You type all the RGB camera as the real sense. Maybe you won't find anything just yet, but the Rust is very, very versatile into just getting some specification sheet and getting some really good code over it. So yeah, that will be my answer. And if you get started now, then you can be among the founders of this, and maybe and maybe together we can go even further than anyone else in C++. Yeah.
I guess I've got some like meta commentary that I think ties into that, and also ties into something that Danny said that I'm maybe trying to wrap my head around how to express this. But one big thing I do see missing from the Rust ecosystem right now that I think really helped ROS as a community like flourish is some of this like standard type definitions for things like sensor, interfacing with cameras or representing transforms, right? These things that there is this like this library of standard ROS messages, and this construct of ROS messages over some interface is powerful for letting people build implementations against interfaces. And Rust shines here with things like traits. But I haven't seen sort of like what the Rust approach to like if you wanted to like build like a ROS alternative, and you're gonna take Rust packages and cargo and just sort of the ease of pulling in dependencies, right? This was sort of something that ROS made easy if you're playing in the ROS ecosystem. And to do the equivalent in Rust, I think would be like a really nice way of approaching this problem. Where okay, we as the robotics community are going to agree on like some standards for how we want to interface between different things, whether regardless of what engine you might be using to do the runtime, or what sensor drivers you might be wanting to use, or what packages you want to work with. Like, it's nice to have some commonality somewhere. And I think like if we were going to take like one lesson away from ROS and not bring all the other kind of problematic baggage from ROS, I think it's not like that standardization of interfaces that would be something that would maybe get us closer there to being able to use sort of the like cargo for package management and just pull stuff together and cobble it together without needing to go over like a ROS IPC mechanism to do that.
So one last follow-up question on that. So is it possible to have Rust similarly integrated like C++ and Python within the Rust and like ROS environment? Because in that way, at least we can have the people around like build faster, because they are very well familiar with how ROS works, and ROS already has C++ and Python, and Rust joins in, so that would be. Is it a good start, at least for the?
Yeah, I mean, I happen to know that like the Rust community is making more strides, year over year of like turning that into like the next like first class language supported by ROS. I don't know exactly when that's going to happen, but I believe that like planning for that is well underway, and there's definitely people within the core ROS development community that are also pushing to get into the Rust ecosystem. Next year's, Rust, it would be great to make sure that we've got someone from sort of that Rust core team or intrinsic here kind of like representing sort of what the state of that effort is. Because as much as I would love to see like Rust just like replace Rust and a lot of that stuff all together, I think we probably have many years of like legacy Rust code to support going into the future.
Thank you.
One of the.
You try to use this microphone. I don't think that microphone is.
Maybe the. I think.
Oh, sorry. Okay. Yeah. It's all there.
Regarding Ross, there are two maintainers right now, and there's a lot that they're undertaking. So if anyone is interested in helping them. As of the industry's adoption of ROS, I think one aspect that makes people sort of hesitant with submitting ROS code is the reviewing. Like you submit code and like maybe like two people in the organization already can read, but ROS. But for them to confidently review that code, we're missing something like Google's C++ style guide or Python style guide, right? So that's one thing. And as of writing robotics code, like in control code, to me at least, what's missing is a clear winner of many fundamental libraries. Like if you want to, use the linear algebra library for C++, you definitely and obviously know what to do. But like with Cargo, definitely there are many libraries there, and we keep researching to go with that. So you keep actually experimenting with them, and like making the decision is taking a lot of time. So those are the two comments.
And
Yeah, Miriam, I'm from Johnson & Johnson.
No, okay, if that's mostly comments or.
Yes.
Panelists that want to follow on.
Do.
No?
Yeah. I think maybe I can talk. I think there's similar comments about kind of standardization, right? Which is kind of standardization of libraries, standardization of messages, guiding style. On this note, I think like obviously Rust is actually still developing, right? Still emerging, and I think that's kind of the thing that's blocking. There's also this question about like standardization of async that we got this morning, that we have a debate on, and I think one of the things is basically there's a thing called the stable AVF of Rust, which is not yet stable, right? So that's why, like, even if we had a message format for images, that's probably going to change. It's still very hard for everyone to use, right? Because then you will have like dependency, and it's kind of a hell for everyone to pin to the right version, right? Same thing for like if everyone pin to an algebra, for example, and then there's a upgrade of version. How do you make sure that you have cross compatibility and backward compatibility and upward compatibility, right? And same thing for async. And so yeah, so I would definitely think that we actually need to get Rust more mature, more stable, and I think with time maybe, and we kind of already see that there's clear win. For example, async, you see that Tokyo is getting more and more traction. Async STD is a bit less, and yeah, I think it's problems that's gonna solve themselves by itself. Like same with Rust ABI, there's a lot of people pushing for this, and I would say that this is an issue for now, but it's not an issue for maybe tomorrow. I think it's kind of something that's going to be stabilized by itself.
I think as a community, we also need better advertisement of our own work. For example, full work. I've never heard of it, right? So like people in the robotics community have learned very well how to use Twitter to over advertise their work. I think
It's called app sign off.
sure. People in the Rust community need to use those tools as well. And like for a library to get to the right audience, it needs a lot of communication, and it's not fully happening maybe in Reddit, but not like everywhere. Maybe also in LinkedIn, I see a lot of LinkedIn posts, but not everywhere that people are reading.
Yeah, do it. Yeah. I'm going to the next question. Oh, no. I mean, I think it's true. I think there used to be like a Rust like hype wave in like 2018, 2019, and we had all the hype. Now it's LLM, so less hype. So we have to make even more nodes than vibe coding, which is difficult. But yeah, I agree that maybe we need more communication. Yeah.
Actually, I do have a question for the rest of the panel. If you don't mind me taking over, that's okay. So I noticed you mentioned using ChatGPT for generating findings for sensors. The rest of the panel, do you use language models for programming? If so, how's that worked out for you? What worked, what didn't, what you like, how you use it?
What do you want to? Yeah.
I mean, yeah, I over the course of the past year, I've certainly started using ChatGPT and Claude and other tools to augment, the coding that we do within Rerun, right? Like where I see it working best for me has been in the context of like a large existing code base, and in particular a well-specified trait definition, right? So that hey, I have a trait, I need another implementation of this trait that that interfaces with some library or some some other thing that I need to use. Pointing Claude at something like that and saying, yeah, implement this trait and make sure it passes the unit test that exists is like a great place where that works. But you do need like this. I don't know. I prefer at least doing this in a context where there's like enough scaffolding in place to keep things from going like completely off the rails.
Yeah, I think I agree with you. I think the like LLM works really well if you have a good example, right? If you have a good definition, specification, you really know what you want, and just like what's kind of like how it's gonna look and implementing it. But I also have like some horror stories about using LLMs and people like submitting pull requests that it's horrible, or even just documentation. And so I feel like actually for Rust, the LLM is not there ready yet, especially when you compare it to Python. But I think it's still very promising in many ways for coding. Yeah, don't know if, yeah.
Yeah, it's a great question. I definitely try it from time to time. I mean, it's pretty clear to tell if you have a task that an LLM is going to be good at, in coding, at least at this point. Has clear inputs, has clear outputs, has probably many examples that it's seen before, like what you're asking it. One counterexample that I was surprised by recently, I tried it mostly out of curiosity. So, was looking at, new code to set up, actually using AD trait that I commented on before. And the idea was to set up, really nice, like kind of distance calculations between convex shapes. So there are very standard algorithms for doing this, like GJK or the expanding polytope algorithm. So nothing new about these algorithms. I would have thought that LLMs would probably would have seen like 50 different versions of this in different languages. I was surprised that every LLM I tried completely failed at coming up with a version of those algorithms that actually worked. And it seemed to me like that would have been a task it would have succeeded at, because it's again, clear inputs, clear outputs, but so tedious to type up like all the math, but there are like corner cases and all of that. but it was very bad at that. So if anybody's curious to like benchmark that over time, yeah, definitely feel free to use that kind of programming task. One area that I feel like LLMs have been completely game changing for the open source tools that we put out is just using them for documentation. I feel like it does so fantastically well, and I'd much rather have AI written, even like overly bland or overly generic documentation rather than no documentation at all, which is typically like my human way of doing things. So that has totally been, well, I would say like 99% of my code is like documented by LLMs now, and I haven't found an issue with that.
This is maybe more of a thought than a question, but like the way I've seen like Rust be successful, like out in the world, is things like rerun where people don't realize that they're using Rust under the hood. Linux kernel development is starting to use it, and we don't know it. Like how do we get to a point where like these batteries included frameworks, ROS, the such, like make it such that Rust is integrated into it so that we can drive further adoption. Because I think we all see the benefits of Cargo in our Rust projects, but people that don't use Rust don't see the benefits. I feel like that's like marrying the two is one of the things that I feel like I don't know that we have anything for, but maybe I'm throwing it at you guys to see.
I mean, I'm actually not. So you're asking like, how do we make the Rust that's being used to improve these things more apparent to the community that's benefiting from them, or?
More like we see the benefits of Rust and
Yeah.
how it's adopted and the ease of use, but like other people that C++ background, we can advocate for Rust, but like they may not be able to adopt it. How do we ease the use of adoption into the existing batteries included things?
Right.
Yeah, I mean, it does just like, in some sense, seem to be happening like gradually, like over time. Like I mean, even just like the example of Rust, right? It's like, okay, that even before Rust gets Rust as a proper like language that's supported, like Xeno as Rust middleware is a gigantic foothold of suddenly the Rust community is benefiting from this Rust core and will become more aware of Xeno, as a result, and potentially like that I can certainly paint a picture where like that, okay, that awareness now leads to, oh, maybe I will do this implementation of a thing that needs to talk to my Rust nodes, via Xeno, just like directly in Rust. Like that becomes more and more plausible, sort of as the tide rises on things that are veneers over that Rust core that's there because of all the benefits that it gives.
Yeah, I think to be honest, I think it's really not that bad of a thing if people don't realize that they're using Rust and like it's just as boring technology, like I think it's kind of like something that we should be proud of, to be honest. Yeah, I mean, I think it's kind of something organic. The reason why people don't use Rust, for example, for using rerun at the beginning, we had a call with Jeremy, and I really wanted to use Rust for rerun, and they were like, well, actually, the thing is, nobody actually used the Rust API, so we just documented it for ourselves, but yeah, you can use it, but most people use Python, but I use Rust anyway. But I think the thing is, I think we're gonna have people using Rust, and we're gonna have adoption when, like Kendall said, there's gonna be enough traction for it, right? And this is how I see the thing. And as long as there's no big traction and people can just use other things like Python, for example, maybe it's not that big of a deal, right? So it's kind of how I see things.
Yeah, I want to add some comments about previous question or comments related like large language model
augmented programming experiment with Rust. Currently I am still a PhD student. I did some human experiments by teaching high school students using Rust and using C++. I found out that before the large language model become a thing, because before GPT is a thing, these high school students who are trying to use Rust for the projects as the first programming language they interfere with, like they found it super hard and they fail a lot. But I do see that after the large language model become more intelligent, if a high school student start to use Rust as their first programming languages, they will perform much better on the project, on the first computer science project they touched with. And this is something that made me wonder, like, maybe it is because of the nature of the Rust programming language can teach students the right way of programming and like eliminate some of the bad habits. I always joke with some of my friends that if you're a C++ programmer, most likely your mind is already being contaminated by a lot of bad programming habits. But I do see that at the stage of large language model, although the grammar of Rust, it is complicated, but with these AI tools, actually, it is not that scary. So I just want to add that comments. Following up on these comments, I have one last question during this panel. The reason I want to bring up the academia industry during this panel actually come up one motivation. It's about education. A lot of people in this room want to learn Rust. A lot of people outside of the room doesn't know Rust. And I think for people who have working with Rust, we already see the benefits. So I'm always asking myself, like, what we can do to equip the future robotist, either as a researcher or engineer, with some Rust skills, and how, from both the industry side and from academia side, how can we do better at this job from the perspective of education? Anyone wanna start?
I can start. So I think, especially in a robotics context, I think it would be good to better communicate the things that Rust can solve right away. So like having specific examples, say in Rust or just, C++ or whatever, where either, a race condition is happening or some memory management issue that comes up, and just having side by side with that, like exactly like the Rust, code snippet that would come up, and just showing even like the error that would come up from the compiler, so it would like never happen. Like just having those like very side by side visual examples would, I think it would be really important for like the education process. Like again, just making it clear that like there are so many bad habits that people have that lead to, an hour of debugging, where I just feel like I don't have that anymore. And when I'm mostly working in Rust. So just making that clear right away in some materials that are easy to share for people in the robotics community, I think could be very useful.
Yeah, I think I will I agree with you, and I'm gonna go. I think so. I started using Rust for the user story because I wanted to make Panda faster. So I helped the guy, like the people who wrote polls. So I started making pull requests to it, and I thought it was really nice. And the thing is, so if you ever use Python, there's probably gonna be a lot of time where you feel like it doesn't really make any sense. You kind of almost kind of like imagining the syntax, right? So if you use Panda, you never know if you're calling a method, you never know if you're copying the data, you never know if you're mutating the data. And I think it's really confusing, and it makes the learning actually very confusing. And it's almost like you have to know by heart Python to be very good at it, right? And I think it's way less the case in NumPy, or sorry, it's way less the case in Rust, where everything kind of makes sense, right? So you want to mutate the data,
you just you just get the ownership, you mutate the data, and then it makes sense, right? And so I think in terms of education, being able to understand what you're doing and not just like pure guessing and using the Python magic, I think is a really powerful tool to understand coding. So yeah, that's my opinion.
I have a few thoughts, but they are a little ill-formed, so I didn't have much time to think about it. I taught an undergrad class in Rust a few years ago. And one of the main things that I ran into was students usually don't have a strong mental model of exactly what they're doing. And they kind of just go straight to the part where they write the code first, and then they figure out what code they're supposed to be writing to begin with. And I think it's easier to get away with that in scripting languages than it is in a sort of strongly typed compiled language. But I'm not quite so sure how to fix that. If you can find better students, then it'll make that easier.
Yeah, so the thing that comes to mind for me when I think about like educational, context is giving people a motivating thing that they can play with, I guess, right? And so again, I'll keep drawing analogies back to things that I think were sort of nice with Ross, right? And Ross, coming with Gazebo and integrations with Gazebo and sort of the ability of like, oh, let me create an environment with a robot and sort of like real lightweight, like, okay, I'm here, I have a simulated robot, I can see what's going on in that simulated robot in RViz, and I can write a little bit of code that starts to control that and do different things. And that writing a small amount of code, but orchestrating an interesting thing that's relevant to you, you're wanting to do something with robotics. And so the faster you can get to, there's at a minimum a simulated robot and it's doing something interesting. Like I think those are the things that serve as good motivations that pull people in and let people sort of continue to close that loop and use this as like a grounding context for that education. And so I think in Rust, it would be great to have something close to that. Like I think Bevy is getting quite close to that, but you need like a bunch of stuff built around Bevy, like just like bootstrapping a Bevy project on its own is still is not very easy. Versus Danny, some of the stuff that you were showing off with Apollo, right? That looked like 100% like the kind of thing that I'm imagining, where I could go with like a couple lines of code and there's a robot, and I didn't have to worry about like the URDF loading and mapping to transforms like that. That's all taken care of, and I can just focus on like a little bit of control code, and I can see that visual feedback, and I have something that I can play with in a meaningful way, and through that play and that experimentation, learn. And so I think things that sort of really lower that barrier to entry and doing something quickly that's interesting to the student, right, is really one of the things to still focus on, sort of making that approachable within the context of working with Rust.
Yeah, we have an audience have a question. Yeah, go ahead.
Yeah, hi everybody. My name is Igor. I mostly live in C++ world. I work for Robotics and AI Institute. We do fun robots. I also teach C++ to everybody on the internet, to companies and whatnot. So my question, it's a common question. So it's related to what you've been discussing right now. And I fully agree that some people just want to hack together things. Like if I'm talking about young students, they usually just hack things together. But my current issue, like I like Rust. I am not an expert in Rust. But at the same time, I have a work and I need to be done with my tasks in the end of the day, right? I'm being paid for certain things. I'm being paid to be an expert, and it's hard for me to do things where I'm not an expert in. And when I start teaching people stuff, I can see this problem already when I teach them C++. Because in the end, the C++ that I teach is very similar to ideas of Rust. Like in Rust, you cannot do wrong things. In C++, you have to control yourself to not do the wrong things, right? So when I teach people the right way of doing C++, many quotes, But when you do that, there is there is always a pushback. And this pushback identified comes from the point that they don't want to do extra work. So the question to you guys, what do we do as a community to avoid the extra work on the side of people that either just want to use something written in Rust or want to learn Rust? Thank you.
That's a good thing.
Yeah, I mean, this is definitely one of those like, sales questions, right? How, like, I mean, I think like for the community that really has leaned in and embraced those things that are extra work, like we are seeing dividends, I think, you know, certainly across industry. I think like I strongly believe that teams that are Rust first teams that are doing a significant fraction of their development in Rust are net winning on productivity. Like those things that seemed hard and seemed like friction end up still saving you more time than they cost you. But you've got to like get over that activation energy, and, you know, and sort of that initial investment is definitely the hard part there. I mean, this is where I do kind of like the Rust model of Rust doesn't give you an option to not do the good, the good things. It takes a much more opinionated, you know, stance on being a responsible software developer. And so it works well when you're in an organization that says we believe in these benefits and we're going to use Rust and live with it, and those benefits will sort of prove out over time. But like for a single individual trying to sell them on that in the absence of like a stronger forcing function, I don't actually know. It's a really good question for how to handle that more micro context as opposed to the macro context in an organization.
Especially to avoid the part of, hey, just trust me, right? Like that's kind of, I think like that's the real question. How do we avoid the, hey, trust me, it's going to be better for you, because people don't trust that somehow, even when you're an expert. It's really annoying, but.
Yeah, no, I absolutely agree. Do you guys have other thoughts on that?
I think in the broad sense, not solvable problem. But in a narrow sense, I think there are a few promising sort of directions going on right now. And it's really all about ergonomics and tooling, making it easier to do the right thing, so to speak. In Rust specifically, I think the two big initiatives are with claim semantics. So trying to make it easier to clone cheap objects like reference kind of pointers without any special syntax. And also the keyword generics, with trying to make programs that are generic over whether they're async or unsafe and so on. And I think if those become easier, we can make it more easy to use and make it faster for people to pick up.
So I think if we take a step back, what we're talking about is kind of like tech debt, right? Technology like code debt that you have to pay back later, right? So if you do like some shitty processing, maybe it's gonna work, maybe someday it's gonna blow up, and so you kind of have this legacy tech debt that you have to pay off at some point. And as you said, like Rust doesn't let you do this, right? And so it makes you do the hard thing from the beginning, right? So you can't just like cut your way in. And I think it's kind of hard, right? So how do we make people do the hard stuff? How do we make people not choose the easy path, which is just like borrow a lot of debt and then go away and then leave the debt for the people? I think it's especially true nowadays with LLM, where you could just write code something, push it, not looking into even if it works, and the crazy thing is like I feel like a lot of students are getting lazier and lazier on those things. And so if you tell them, well, you're gonna learn Rust and you're gonna fight with a board checker, or you can use Python, you can write code the whole thing and not care about it, and maybe it's gonna work and maybe you're gonna pass the test, right? And I think it's yeah, so it's very hard, right? It's always been hard to get people to do the hard stuff over the easy stuff. But then I think it's also where, like for me, I'm at this point where I'm like, well, here's the door, right? So if you don't want to do the hard stuff, just leave, because I mean I don't have time. But but I think this is also where, you know, it's a good way to get the good people in, right? As well, like we don't have like infinite time. And like there's some people there's some students who want to learn the right way, right? And so I think for me it's more like this thing. Yeah.
Oh, I'm gonna throw in one more. I'm just standing over there. Yeah.
Yeah, I had something very brief to add. I agree with everything that's been said. So one, it's also worth thinking about like what's the extra work we're actually considering here. Like I don't think anybody looks at Rust and they think of like, oh, like marking variables as mutable or not mutable. Like that's not a huge amount of like extra work. But I think there are situations that I've seen where like kind of beginner Rust programmers, they spend like 3 hours trying to put something together and they think they've like kind of programmed themselves into a corner, like they have some design for something, and then the compiler is like, oh no, you have an immutable reference or ownership to this, and then oh, you can't also have a mutable kind of pointer to this. And I think there are some programming patterns that we can make more aware, like, oh, you just wrap this in like an arc mutex and then you're fine. Like where the work that you put in was not like a waste, because like I think a lot of people think the extra work is like unwinding and then trying again. And just making those programming patterns more evident for Rust. Like that extra bit of learning and that like just few extra keystrokes can just fix everything. And Rust, to me, like kind of many years into working with it, it doesn't feel like extra work. It's just learning kind of the right wrappers to have around different variables just to make everything click together in a way where it's more or less guaranteed to work. So just getting more novice programmers in Rust to realize that that extra work is more just an extra layer of the learning curve that's harder to find, like in the documentation or through conversation, and just it's our job to make that more visible and evident.
So yeah, one like additional thought I had on this, right, and sort of as this is sort of academia and industry sort of coming together, sort of talking here. I do think this is probably an area that is kind of easier to solve from the industry side of things than from the academic side of things. Like in an academic context, you do kind of have to sell people on doing the right thing. And I think if Rust really is the right productive language to be using for these things across industry, like we will see forces that ultimately lead to more companies sort of advertising positions, hiring for Rust programmers. And I think over time, as you see that, if we see that shift of just more of the robotics jobs that are out there require Rust in the job posting, in the resume, like that can also be a bit of a forcing function for like, why should you do this in Rust? Well, you should do this in Rust because you want a job at some point in the future. And like everyone that's hiring robotics engineers, are hiring people in Rust. We're not there yet, but but I think we could get there. And I do think that sort of to that first point I was making, that like teams that work in Rust are more productive. Like there is like a financial incentive and financial reward for companies leaning into these like Rust first projects and Rust first at least like units within organizations, if not entire companies. It's a heavy lift to go all Rust for a company, but I think new teams and new projects spinning up have lots of opportunities to sort of lean in there and create more of a demand across the community for people to work in Rust.
Okay, I guess this is the end of the panel. So everyone, can we have a round of applause for all the panelists? Thank you. So I think we are closing to the end of this workshop. So I will make closing remarks just to summarize the items that we discussed and learned, and maybe there's something that we as a community should work on as the next step. We can keep it. Yeah, before I make my closing remark, this is an advertisement. So I created this Rust for Robotics Discord
several months ago, there are already quite a lot of people joining Discord. This is a pretty active Discord. So if anyone would like to learn more about how to use Rust for robotics, I want to discuss, or just chat with us. I think this is a. Oh, okay, wonderful.
Yeah, I think.
Oh, okay.
There you go.
All right. I hope the QR code scanning is working. So yeah, so this is a pretty chill space. So feel free to ask any question. There's no like you are a newbie, you are an expert. There's no any discrimination there. So just feel free to join this cohort. So while everyone's scanning the QR code, I would like to summarize a little bit what we discussed about today. So we heard a lot of successful story, both from industry and from academia. So we know that Rust has a lot of beauty. It is fast. It guarantees memory safety. It has a pretty good tooling system that is easy to use. It can also help the new beginner to learn a better programming habits. And also we see a trend that this is possible that we can start to adopt the Rust, but not like discarding the entire code base running on legacy system or in C++ or Python. So we don't think that this is a chicken or duck problem. You don't need to pick sides. We also definitely see conflicts. Just as this morning during the panel, we are debating like, oh, which is the correct way to do async? And also during this afternoon, we also discussed that, oh, we have a lot of linear algebra crates, but what is the right one to use? We need to still do our own research and study them. I personally think this is not a bad thing. And that means that this community is growing, it is active. I'd rather stay in a situation that people are actively like competing rather like it is like a dead zone, like nobody are like doing new thing. I think this is actually a really good signal that people are innovating. We also heard a lot of difficulties from the audience and also from the speaker that adopting Rust, it is not easy. I need to say that it is not an easy way, but with the community's effort, with a growing community and with the help among the community, I think that we can grow this community even larger and help new members to adopt Rust and appreciate the beauty of the Rust and make everyone's life better. I would like to go to the first slide. I want to talk a little bit about why I used this title for this workshop. Originally, the workshop title is just for Rust for robotics. But why we are saying building robust foundation for tomorrow's autonomous systems. I want to share a little bit personal story. Sorry for taking everyone's a little time, but the reason I start to learn Rust, the real motivation initially is that I feel like right now the robotics software ecosystem has some issue. It's a little bit broken, it's a little bit shattered, it's functioning, it's definitely working, but something is not right. I see that with more company and academic lab are like adopting Rust to rebuild things. It looks to me like it's like a reset point. Like we probably can take this chance to solve some legacy problem. But this is only my personal opinion, and I don't think that's completely right. I don't think we need to discard the old system. But I think that with this new trend, with this nice property of Rust programming languages, tomorrow's autonomous system need that. We need to let more people know that Rust could be helpful for robotics. And also we want to make the journey for the new members easier. So growing the community and making the entire ecosystem better, that is my original true motivation that I want to create this workshop. And I do really hope that Rust could be one of tiny block for tomorrow's autonomous system. And I think that we need everyone's help on that. At the end, I would like to thanks again to all the invited speakers from Jeremy, from Angelo, from William, from Haishen, from Hockey, from Clayton, and from Pentalus. I think he's on Zoom right now, and from Roy, and also from Daniel. Thank every speaker for helping us making these nice talks. Let's give a round of applause for them. And also, I would like to thank all the organizers to help us make this workshop successful. I will say this is not an easy task. Making a Rust for Robotics workshop into ICRA, I actually didn't imagine it will work out when we submit the proposal. The entire proposal, we actually find like finish in 2 weeks. It is a miracle. So I want to thank Ray for the session chair, and also he helped a lot during the proposal already. We'd like to thank William. He made a lot of comments during the proposal session, help us to make it more robust and help convincing the ICRA community that this workshop is relevant. I want to thank Haishen, helping also during the proposal session and also for helping chairing one of the panel. I want to help Joe Hong. Currently, he's not here. He's making another poster session in another workshop. He'll help a lot for all the technical support and help setting up the website. I want to thank Kuniko for helping us taking all these pictures and making a lot of drafts for the social media posts. That's really helpful to let more people know we are here. And also I want to thank my advisor, Giuseppe Loiano from New York University. He gave a lot of advice for a PhD student who hosts the workshop for the first time. So thank everyone to make this workshop happen.
Thank you, Yang.
Thank you. Yeah, so I think I left a little bit of time, so I really encourage everyone to like talk to each other, make some connection, because that's what is most important for the workshop. Yeah, thank you so much. Yeah. For all the speakers and workshop organizer, I think we can take a picture.
Yeah.
Yeah, that would be great. Yeah. Like one of the one-on-one robotics
I mean, I think it's like that. Those are the things where like roughly the building so everyone agreeing to that.
One thing I want to add.
Okay.
The worst.
Look at curiosity, gather for a picture. I think.
Rust. Yeah.